Log on, tune in, find out. Another good idea from Cambridge.
Let's continue. So to recall, there was a chapter 0, let's say, introduction. First one was on mean field limit. And second one was on the Vlasov-Poisson equation. So that's what we were discussing last time at the end of the course. And so I'll try to do this. And the goal is to do the linear damping. And the statement of the nonlinear result and some comment. Let's say the main result the nonlinear damping. And of course feel free to interrupt me and to ask questions. So first we were discussing about the Vlasov-Poisson equation the last time. So maybe just some comments before ending this chapter. So let me recall. So still chapter 2, some comment section, let's say. So let me recall that I take this general form for this equation, for the equation. And then F is the self-induced force field, which is given with this notation as a convolution of the density. Okay. So that's a nonlinear Hamiltonian PDE. And just some comments. In the last course, we had discussed some the structure due to the characteristics, the reversibility of the equation. Also, we had discussed the invariance, energy invariant. Also, the Casimirs, all the movement invariant that we can build for this equation. Also, the equilibria. The conclusion we can draw from all of this is that it is extremely complicated because, I mean, if we look at the main question we can ask, we ask usually for PDE. Main question is how many equilibria? Here the answer is infinite. Which are stable and unstable? While it remains open for most of the cases. And if we try to go to the more detailed question we want to ask usually for PDE, which are attractive in a sense? Then again, it's open in general. To all this natural question, let's say at now mathematically, so there are many yeah, this is what we need to define what it means in some sense. Well, you could imagine it has not been done for this equation. You could imagine some abstract invariant measures in the space of solutions, like what has been done for Schrödinger equation by Bourgain, and like what have been tried for 2D Euler, for instance. At now, nothing is known for this equation. Nothing like this. So, to all these questions, well, the only answers so far that I know are first, the orbital stability theory, which try to answer this question in Lebesgue spaces, so in low regularity spaces. So I won't speak so much of this theory, which is quite nice, but very different from what I do. So the so-called orbital stability theory. Which is associated with many names, many physicists, many mathematicians. Try to answer question 2.2 in Lebesgue space with low regularity. And our work try to answer the question, altogether question 2 and 3. So our work is an attempt to answer 2 and 3 close to homogeneous equilibria. So for all these questions, that's really very few information we have at now. Well, importance of our work, let's say, is that it's the first result. This is the first result of non-entropic relaxation for a confined many particle system. So we will see some precise mathematical definition in the next chapter in the linear case. And this is something which is very important in the applications. Let me just recall the two main modeling use of this equation. These are plasma and galactic dynamics. For plasma, there is the well-known sort of stabilization effect in your confined plasma that is homogenizing very quickly, much quicker than the time scale of collisions. And for galaxies, it was argued by Bell in the 60s that the relatively low time scale, observable time scale in terms of, not by a human, but in astronomic scales, at which galaxies are reaching what seems to be an equilibrium distribution in space only, is much lower than what you could expect from an entropic relaxation. In a gas of star composing a galaxy, if you try to compute the time scale at which collisions are supposed to increase entropy and bring something like an equilibrium, it would be much larger than the age of the universe. That was one of the arguments of Bell to argue for a Landau damping phenomena for galaxies. Okay, and he was also calling this violent relaxation. Well, we don't know at now how to do math with this, but let's. Okay, it's really supposed to be related. And well, let me stop on this comment. So this is the first result of this kind, and this is really, I want to emphasize that it's really working for a non-dissipative system, and it's not using any additional randomness noise that you would add to the evolution to explain what happens, which is also another line of research, which have, well, quite important, that you could relate also to the so-called coarse graining theory in physics, which is a way to add noise also in a sense. Okay, so let's stop with this. And let's try to understand the Landau damping at the linear level. So in this part, I will start with the free transport equation for which Landau damping just amounts to what is called phase mixing, usually in dynamical system. And then I will try to show you the, not exactly as Landau was doing, but the computation on the linearized laws of Poisson, which led Landau to this prediction. Okay, so let's start. And let me add a word of introduction. The mathematical structure discovered linked with this phenomena discovered by Landau and Vlasov. There is a very nice structure behind this phenomena for the linearized laws of Poisson, is the fact that you will see in the computation the linearized laws of Poisson equation around some homogeneous equilibria decouples the evolution of each frequency of the density. So by density I mean space density, okay, rho. And that is what will make everything work in the computation. So we will show that from this equation, once you linearize, you can close an infinite set of equations on the frequencies of the density. So let's start with the free transport equation. So the free transport PDE just mean you write the Liouville equation for particles going in straight lines. So this writes like this. And it is extremely useful to understand, even if the equation is looks rather trivial because you can solve it explicitly, it's extremely useful to understand the estimate first on this equation, because you can say roughly that all our paper is about trying to show that the estimate valid for this equation is still valid first for the linearized Vlasov Poisson and then for the full nonlinear Vlasov Poisson. And this is a correct statement. I mean, we really want to show that all the estimates true for this equation still remain true for Vlasov Poisson. So, property, as I already said in the previous courses, property of this equation it differs a lot depending whether you're in the whole space for x, Rd, or in a confined case. And as I said earlier, as a confined setting, I will always use the torus to have maximum simplicity. Okay, so in the whole space, the asymptotic will be driven by dispersion effect. In the torus, on the other hand, the asymptotic will be driven by ergodization of the trajectories in the torus. So, and there will be an homogenization due to phase mixing. So let me draw a picture for this phase mixing. Assume V and X are 1D. Okay, and you start at time 0 with, let's say, some characteristic function supported by this line. Okay, in the plane X and V. Now you look for a later time, and don't forget that you're in the torus in X. Okay, so you suppose that, sorry, that's the line here. Suppose that up to the, when you reach this line, then you go back to this line. Okay, you have periodicity in X. Then after some time, what you will observe is something like this. Okay, you don't go to higher velocities, velocity is preserved, but you see that the point moves depending on which velocity they have. But then there's a point where you will reach the bounded of the torus, the boundary of the torus. After some time, you will create something like this, and after a long time, you will have something like this. That is the phase mixing effect. Okay, and so in the end, if you take two particles which are close here, they will be more or less randomly distributed, one in terms of the other one. That's really an ergodization property. So just, I will not use it, but what do we use really in terms of structure, in terms of dynamical system structure behind? We use that we have a system in action angle variable. So if you don't know, that's absolutely not necessary for the sequels. Just writing it here. So imagine a completely integrable system, dimension 1 and 1 position, 1 velocity, for instance. You can rewrite it in this form with an action variable and an angular variable. What we really need is that the speed, the angular speed, that's the speed in the angle, really varies with I. Okay? What we need this kind of stuff. This is related in dynamical system to heterochronous completely integrable systems. Okay. Let me still do a picture for this in this variable. Okay, no, let's not say like this. Okay, you have possible trajectories here, described by an angle, and they are labeled by the action variable. What you want, when I say this, you want that the angular speed at which you travel along this trajectory really change when you change trajectories. If you travel orthogonally and you traverse, you cross each of these trajectories, you want really the angular speed to be changing with I. Okay, and that's a rigorous assumption. That means if you have this, assume for instance it's strictly increasing in this annulus. Okay, between this trajectory and this one. It means if you start with some characteristic function of this small region here, how will it evolve? After some time, it will begin to deform like this. Why? Because angular velocity here is bigger than here. After some time again, deform more, and after some time, it will spiral in your annulus. This is the equivalent in this setting of this ergodization property. Just to make something a bit more general, what is different here as compared to here is that here you have no, trapped trajectories or a zero measure set due to the fact that it's a torus. As long as you have a property on the coordinates of v, like irrational and free over q as a vector, then you will never come back to the same point. Okay, you don't have closed trajectories like in my example here. But the idea is really the same. And just some comment to put a word on this. What does it mean? This is really anharmonicity. Why? Because if you consider the usual harmonic oscillator, the linear harmonic oscillator is a constant here. Okay, and then you travel with the same angular speed on all your trajectories. And if it's a constant, then of course you will never see this ergodization property. If you start with my characteristic function here, it will stay the same and just move around indefinitely the same way. So for this, as a sort of moral, for this very simple linear PDE, to observe this ergodization, we need that it's coming from an ODE which really has genuine nonlinearity. And harmonicity is a way to say that your ODE you start with is really nonlinear. So you get the point. I mean, this mixing property for this linear PDE comes from the fact that this linear PDE is associated with an ODE, the characteristic ODE, and you need some nonlinearity at the level of this ODE. Okay, so now let's give a real proof, not shaking hands, of this phenomenon. So, free transport equation can be solved. Of course, you can solve it explicitly. F at time t is just given by the initial datum, where you go backward the characteristic. Okay, so now let's go to Fourier. Let's Fourier transform f in both variables. So as a general rule, I will use the tilde when I Fourier transform in both variables. Okay, and I will keep the usual hat notation when I Fourier transform only in x. But I will say it again, because we will have both, so it's good to distinguish. So my dual variable are called k for x and eta for v. Remember that v is in the whole space, so eta is also in the whole space, is a continuous variable. K is discrete, because we start from the torus. And then, of course, it's the usual definition. With just one subtlety. It's just the fact that from now on, I forget the size of the torus. Because if you want to keep track of the size of the torus, you need to keep here 2 pi over L, where L is the length of the torus, okay? But let's normalize this once for all. It plays a role and then in the exact constants, but I will give you the formula when needed. So, in Fourier variables, what does this explicit solution means? So you have several ways to reach this formula. Okay, so several ways to prove it. Either you just Fourier transform the solution here. Okay, so you and you use the change of variable capital X to be x minus vt. Second possibility, you just Fourier transform the equation. And in Fourier variables, the equation looks like this. Okay, it has exchanged the multiplication variable and the derivation variable, and you have a minus coming from the fact that you have I to the square. Okay, so you end up with this formula. Then the proof of the effect on the right is finished as soon as you have a bit of integrability, as you are able to define these Fourier transforms. Okay, so what can we deduce? Of course, the zero spatial mode is preserved. You can see at the level of the Fourier solution. Which is coherent with the fact that if you integrate in x the equation in the original variable, you get that it's preserved with time. And also, so that is not changing, and more or less all the other modes will go to 0 for fixed k eta. So now if you fixed eta and k non-zero, then this Fourier transform goes to 0 with the rate given by decay of the Fourier transform of the initial data in the second variable. So what I'm doing now is I'm giving you a really stupid proof in Fourier of some very simple fact you could have done in another way. You're recovering a proof of weak convergence to a constant that you also could have done by Riemann-Lebesgue lemma. Sorry?
The case where t goes to infinity.
Yeah, sorry, of course. And minus infinity as well. Yes. So in particular, what we see is, we will use this phenomenon all along our paper, is that this transport semigroup is converting regularity into decay, which is not something new in math. That's exactly the basis in Riemann-Lebesgue lemma. You exhaust the regularity as time goes on because it's transformed into oscillations and so on, and you produce a decay in weak sense. Why is it weak? Because of this. It's for fixed modes. Okay, but then if you take some given time, you can always find a couple of modes which will not be close to 0, which will be of order 1. And now it's you get a weak convergence because, of course, if you integrate against some test function thing that is very regular, meaning it's a cutoff in frequency variables, then you can use for a fixed number of frequencies this convergence to 0. So we can represent what's going on. Yeah, before maybe let's give some rate. So what is the rate in this convergence? So it's a mode by mode convergence, and if f initial is analytic in V, in the velocity variable, then we get exponential rate. If, for instance, f initial is in some Sobolev space, let's say WS1 for instance, in V, then we get polynomial rate related to S, whose exponent is related to S. And you could go to lower regularity up to, older would be enough. I mean, you can go to very low regularity, but you pay it at the level of the rate. So, a schematic picture of what's going on is that in Fourier space, well, I like a lot this picture because it resembles the shear flow in fluid mechanics. And it's well known that Vlasov-Poisson and 2D Euler share a lot of structure in common, so that's, even if it's just it's not a rigorous comparison, but so what's happening in the frequency space is that you have a cascade of energy flowing. The energy is going, let's put it like this. Okay, what it means is that you look at several times. Okay, T1, T2, T3 for different K modes, and you see the energy which is flowing like this from low frequency mode in velocity towards high frequency mode in velocity. And it moves faster and faster as K becomes bigger. So this is really a sort of quantified way of saying that the Vlasov, the transport equation, creates oscillation by filamentation. That's a sort of quantitative way of saying this. So let me now explain what you can deduce on the density and what is filamentation. This is related to oscillation in velocity, which is usually called by plasma physicists filamentation. The name filamentation comes really from the fact that it looks like filaments, thinner and thinner. And it is observed very well in aurora borealis, something like this in English. I mean, in phenomena with plasma, it is observed and creates beautiful, very thin structures. It is observed in plasma simulations and so on. Let me give you just a sort of trivial mathematical idea of it. Of course, it's on free transport, but trust me, for a while, it is still true for the linearized Vlasov, and it will be still true for the non-linear Vlasov. It can be seen as a consequence of our theorem in some sense. Filamentation is the fact that if you look the exact solution written on the left of the free transport equation, and then you ask about regularity. Regularity in X first. Then that's easy. It's clearly preserved. Okay? Because if you differentiate in X here, then you differentiate in X the initial data. And if you have a lot of regularity in X for F initial, then it's preserved. Now regularity in V is deteriorating. And it's, I mean, there's only two situations. Either F initial is homogeneous. So if F initial does depend only on V, then it's preserved. But we know it already because it's an equilibrium.
But is, if f initial depends only on v, then it is stationary solution.
Yeah.
And it stands.
That's exactly what I was saying. It's an equilibrium, so that's not a big surprise. So all the other interesting cases is when it really depends on x, and in this case, the gradient in v of the solution at time t grows like linearly in time. And if you go to the second gradient and you look at iterated gradient, the L derivative, then you get T of L, T to the power L. And if you would go to analytic norm, it would grow exponentially. And there's nothing to do against this. I mean, that's an exact computation. Whatever you do, even if the initial data would be very small, after a long time, the linear growth would take it over. So that is the source of a lot of difficulty for this equation, that the semigroup creates oscillations. Now let me say a second thing. So let's say that was first remark. The second is that even if it does not mean, it's not very meaningful at the level of the linear transport equation, we can ask about the density, as we would do for Vlasov-Poisson, because force field is created by the density. And then a very nice feature, I emphasize, this is like this, and then here, let me emphasize that, Ft goes weakly, okay, I'll write it there, the convergence, you can deduce, I said it but I've not written it, the convergence on the distribution Ft we obtain is that Ft is weakly converging as t goes to plus or minus infinity toward its space average, which is the same as the one of the initial data. So I will always use this notation, maybe not fully conventional, but okay, this will mean, be careful, only average in x. Okay, so this is just a consequence of these 2 points, because the zero spatial mode is preserved and all the other one goes to 0. So in weak sense, if you integrate again a text function, you obtain this convergence, which is quite good, because you see that you converge to something which is stationary, but in weak sense. But now if you go to the density, so the density rho of t and x, by definition, is the integration over v. Okay, if you go to Fourier of rho, frequency k of the Fourier transform of rho, this is the zero mode in v, that's the average. It is by definition Fourier transform of f at t k0. Okay, and now if you, it's still written there, the formula which is boxed at the top. So you deduce from okay, I just rewrite it. You see, I'm starting from this. And then I deduce that rho, maybe my rho look a bit like my f, be careful. Okay, I will do this. So my rho of tk is this strange Fourier transform of the initial data. And now this is strongly converging to 0 for any k different than 0. Of course, for k equals 0, we found again that it's preserved, but it's not a surprise, because remember, integral of x, the 0 mode is just the integration of rho, means integration of x and v of f. And we know total mass is preserved. And now for k different than 0, each mode goes to 0 with the rate, with rate which is the decay of f initial in the second variable in Fourier. To be more precise, I will write it here. If, for instance, let's now make a real estimate. For instance, assume f initial is analytic in V. Analyticity will be a very natural assumption in this context because it was used by Landau. I think that's the first reason for which everybody tried to use analyticity. And also it appears that in our study we really need an enormous amount of regularity like this. But of course this is because we were not good enough to go to lower regularity, but at least we needed in our method. So f initial is analytic in V, which means it's Fourier transform, and let's say uniformly in X. So this sentence means that its Fourier transform decays exponentially in the second variable. Okay, so now I'm just making an example of what you can deduce from the left blackboard. Then you deduce from this that rho of tk is less than constant exponential minus kt. And also the t is absolute value if you want this statement to include the convergence for t going to plus infinity and minus infinity. Okay, so you see that in particular since k is discrete, you apply this to any k different than 0 and you obtain that rho of t minus its average and you can estimate in any Sobolev norm, whatever you want, any regular norm will go exponentially to 0. Maybe you lose a bit on the lambda, but it's not important. So for this linear transport equation, what you see is that there is ergodicity of trajectories. It's related to heterochronicity of the dynamical system. Going to Fourier modes, we use that it is converting regularity into decay, thanks to this ergodicity. And then we use this to prove that the full distribution is going weakly to 0. It's going weakly to a velocity-dependent distribution. And now, going to the observable density, we deduce that the density is going strongly to its average.
And the average is rho. The average in what time?
In space.
Space.
Yes. Yeah, be careful with this notation. It's not a notation of average with time. And this is preserved with time. That's what?
Mass.
Yes, that's the mass. Yeah. Yes, just because when I write like this, you think to the fact that it's the 0 Fourier mode. So should I make the, let's make the break now.